Welcome to topic 2.3 of our course titled The Agency. In this module, we are diving deep into the cognition and reasoning, specifically focusing on the decision making process of an AI agent. This session is designed for software engineers who are preparing for high level system design interviews at a major technology companies. Our primary objective today is to explore how we can transform raw large language model into autonomous digital investigators. We'll move beyond simple text generation and look at the engineering patterns required to build reliable agents. We have a lot of ground to cover, including the nuances of prompt engineering, advanced planning algorithms, and strategies for making decisions when faced with environmental uncertainty. Think of this as a folder as a confidential briefing on how to architect the mind of an agent. By the end of this session, you'll understand the underlying mechanics that allow an agent to interpret a complex goal and navigate through the sea of data to find the right answer. Let us open the case file and begin our investigation into the cognitive stack of agentic systems. Let's start with the fundamental analogy to help bridge the gap between a standard large language model and a true agent. We often think of these models as high potential interns or the rookie on a detective force. They are undeniably brilliant and they are incredibly fast, and they have essentially read every book in the world library. However, they often lack what we call as a street smart. The problem is that if you simply bark vague orders at a rookie, they'll often fail. Without a specific protocol to follow, they might hallucinate or may take wrong turns. You do not necessarily need to rewrite their underlying architecture or rewire their brain entirely. Instead, you need to teach them how to think like a seasoned detective. We achieve this by shaping their cognition through three essential pillars. First is prompt engineering, which is the briefing or how we talk to them. Second is planning, which is how we broke down a complex case through a goal decomposition. Third is handling uncertainty, which involves acting correctly when the environment is foggy. We use mathematical frameworks here, like partially observable Markov decision processes to manage this risk. This foundation turns a raw mental model into a reliable partner. Every successful investigation comes back to the mental model of the loop. This cycle is the heartbeat of any agentic system. It involves seeing something, which is perception, thinking about it, which is reasoning, and then doing something, which is the action. If any part of the chain breaks or fails, the bad guy gets away and the task remains incomplete. The agentic loop is the cyclic process where each step informs the next. We can break this down into three core components. First, we have prompt engineering, which we call as the policy. This involves shaping the inner thought style of the agent and defining its rules of engagement. Second, we have planning, which represent the strategy. We use explicit algorithms to turn open-ended, high-level goals into structured sequences of tasks. This often involves hierarchical task networks or goal task networks. Third, we have uncertainty, which is the risk management side. We must inject probability and value awareness into the model to help it handle noisy environments. By mastering this loop, you ensure that your agent can perceive the clues, use logic to find the truth, and eventually perform the best through effective action. In this section, we explore the interrogation phase, which is known as the prompt engineering. A prompt is an agentic context, not just a simple question or a chat message. You must view it as a program or a configuration file. When you write a prompt, you're not asking the model to chat with you, but you are configuring its operating policy and setting the rules of the room. A functional definition of a prompt is that it configures the temporary policy of the large language model. It dictates how the model interprets goals and how it chooses specific actions. The exact same model can behave as a passive chatbot or a sophisticated tool using agent depending entirely on how the prompt is engineered. There are two primary levers we use to adjust its behavior. The first is few-shot prompting, which involves loading specific patterns and examples directly into the working memory of the model. The second is chain of thought, where we force the model to generate a stack trace of its own reasoning before it attempts to execute a final action. This ensures the model thinks through the implication of its decision before committing to them. Let us look at our first piece of evidence, which is a fusion prompting. In the world of investigation, you do not just tell a rookie to go and catch the guy. Instead, you show them files of old successful cases so you can learn the rhythm and understand the policy of the department. This mechanism is called context learning. It allows the large language model to generalize a decision boundary from a provided example without requiring any underlying weight updates or retraining of the entire neural network. There are several best practices you should follow when using this technique. Usually, a set of 2 to 5 high quality examples is sufficient to set the pattern. You should focus on diversity by showing different types of tasks to prevent the model from overfitting to a single scenario. It is also very effective to include negative example, which shows bad behavior to clearly carve out what the agent should not do. The ultimate goal here is to shape behavioral policy. You want the agent to learn when it is appropriate to use a professional tool versus when it should answer the user directly. We are shaping behavior, not just formatting output. Next method in our toolkit is chain of thought or thinking it through. A rookie investigator often likes to guess because they want to impress the chief with an instant answer. As an engineer, you have to stop that impulsive behavior. You must enforce them to show their work. In the context of agent, chain of thought is much more than just an explanation for the user. It is a vital control flow mechanism. It forces a stack trace of reasoning to occur before any execution happens. The implementation follows a clear three-step process. First, the model generates a reasoning trace of its internal thoughts. Second, it derives the actual action from that trace. Third, you have the option to hide this internal monologue from the end user while keeping it available for the agent and for the debugging purposes. The most common prompt used for this is the phrase, "Let us think step by step." This simple instruction is surprisingly powerful because it prevents the model from jumping to plausible but ultimately incorrect action. By slowing down the processing and adding internal steps, we significantly increase the reliability and accuracy of the final output. We now move to the Heist scenario. To understand why we need explicit planning, imagine your objective is to get the gold from a bank vault. You cannot just walk through the front door. You need a detailed plan which involves disabling the laser, distracting the guards, and drilling the lock. For an AI agent, implicit thoughts are not enough because complex goals like setting up a data pipeline are too large for a single inference turn. This is why we must move towards explicit planning. Implicit planning occurs in the head of the model within the chain of thought block. Explicit planning, on the other hand, involves representing plans as a structured object such as a JSON or a direct acyclic graph that persists through multiple turns. This allows the system to maintain a long-term state. The core logic shifts from trying to do everything at once to simply doing the next right thing. By externalizing the plan, the agent can track its progress and handle complex dependency without getting overwhelmed by the scale of the task. This blueprint becomes the shared state between the planner and the executor components of our system. The hierarchy of planning is best explained by the question of how to eat a whale. The answer is one bite at a time. In system design, we take a massive compound job and break it into smaller compound tasks. We then recursively break these down while we reach primitive tasks, which are atomic actions that the agent can actually execute. This is known as the hierarchical task network. The structure consists of a compound task, which are abstract goals like deploying an application. These are supported by methods which act as recipes or logical paths to break these goals into subtasks. Finally, we reach primitive tasks, which are actions like git push or writing a specific file to a directory. During execution, the planner recursively decomposes the goal until only primitive tasks remain, and then it executes them in a logical order. This method of recursive decomposition ensures that even the most daunting objectives are addressed through a series of manageable steps. It provides a clear roadmap for the agent to follow and allows for easy verification of each step in the process before moving on to the next. In the digital world, our operational blueprint is JSON planning. We treat the plan itself as a structured JSON object. A critical design pattern here is the separation of concerns. The planner component writes the code and the plan while the executor component runs it. We should never let the architect lay the bricks. By using the large language model as a hierarchical task plan network planner, we ask it to output structured plan in a JSON format rather than a free-form text. The architecture pattern consists of two distinct prompts. The planner prompt is responsible for outputting the plan structure and should have no side effects or external interactions. The executor prompt takes a single primitive task from that plan and uses available tool to achieve the plan. This creates a loop of planning and refining and then executing. This separation of the architect from Mason uh, makes debugging significantly easier and prevent the system from taking hallucinated actions. It ensures that every move the agent makes is grounded in a pre-approved plan that has been validated for logical consistency before even the first API call is ever made. When we look at the patterns of investigation, we realize that the agent must be flexible. Sometimes you map the entire tree from the beginning, but other times you only plan the next three steps because the situation is fluid and unpredictable. We use three primary patterns for this. First, are top-down objective trees, which are recursively breaks a goal down into subtasks until the path is entirely clear. Second is the receding horizon pattern. Here the agent generates a plan, execute the first two steps, observe the new state of the world, and then replans based on the new information. This is essential for dynamic environments where the world changes as the agent reacts. Third are goal task networks, which plan abstract high-level goals, such as ensuring scalability with concrete tasks such as running a performance benchmark. This allows for greater flexibility in how goals are met. Depending on the complexity and stability of our environment, you must choose one of these patterns for a combination of, or maybe a combination of them. The key takeaway is that the agent must be able to adapt its strategy as it gathers more information and move closer to its final objective. In reality, the streets are often foggy and decision making becomes difficult. While a classroom or a lab environment is safe, the real world street is not. APIs fail, data is often noisy, and sometimes users even lie. You do not always exactly you do not always know exactly where you are in the state space. You only know where you think you are. This requires a shift from deterministic planning, where a state is assumed to be known, to a stochastic decision making where the state is hidden. There are many sources of uncertainty, including API rate limits and network latency and incomplete user requirements and model hallucinations. The fundamental question for the agent change from asking, well, the agent changes from asking what sequences reaches the goal to asking what policy maximizes the expected value. We are no longer looking for a perfect static path, but for a resilient strategy that can handle unexpected obstacles and noises. This mindset shift is critical for building agents that can survive in production environments where things rarely go exactly according to the plan. You're building a system that can reason its way through ambiguity and make the best possible choice given the available and often imperfect information. To handle this ambiguity, we use a concept called as the hunch or partially observable Markov decision processes. Imagine you see a shadow in the dark alley. Is it a contact you need to meet or is it a gunman? You do not know the actual state for sure. You only have a belief, which is a probability distribution over the possible states. In large language model agent, this belief state is approximated by natural language summaries and confidence scores. This allows the agent to act based on his best guess of the truth. Crucially, this leads to information gathering actions. These are actions chosen specifically to reduce uncertainty rather than directly advancing the main goal. For example, the agent might decide to ask a clarifying question to the user or check a specific log file to confirm its assumption before taking a high-risk action. By prioritizing these information gathering steps, the agent can clear the fog and make more informed decisions. This moves the agent beyond blind execution into a state of active learning where it constantly updates its internal belief model to match the reality of the environment it is operating in. Every move an agent makes has a cost including time and money and tokens. Therefore, the agent must be able to perform calculated risk assessment. Before moving, it should weigh the potential cost against the expected payoffs. You do not want to burn $1 million tool on a 10-cent lead. We implement value-oriented selection by approximating the expected value through a rubric included in the system prompt. This rubric typically focuses on three axes. First is impact, which asks how much closer this move brings the agent to the goal. Second is cost, which accounts for latency and tokens and API fees. Third is risk, which considers the consequence of a failure for this specific action. We use a decision template that instructs the agent to rate its candidate actions on these axes before any further execution. This encourages the agent to be economically rational and strategically sound. By quantifying these factors, the agent can choose the most efficient path forward and avoid wasting resources on low value or high risk activity. It turns the agent into a responsible steward of the computational and financial resources it has been granted to achieve its mission. Let us walk through a big case in system design. Suppose the chief wants a scalable notification system. We follow a clear four-step process. Step 1 is interpreting the goal. The agent clarifies the requirements, including non-functional ones like scale and latency targets. Step 2 is building the hierarchy using a hierarchical task network. The agent decomposes the goal into tasks such as architecture design and component building and failure mode analysis. Step 3 is identifying the unknowns through the lens of a partially observable Markov decision process. The agent identifies that it does not know the expected throughput, so it chooses an information gathering action such as checking historical logs first. Finally, step 4 is execution and refinement. Based on the logs, it found the agent might refine its plan to include database sharding to meet the scalability requirements. This walkthrough shows how all the cognitive pillars we have discussed come together in a real-world engineering task. The agent interprets the need and structures a plan and identifies risk, and eventually execute a refined solution that is grounded in data and logical reasoning. This is how you build a MAANG level autonomous system. We have reached the end of our briefing. and the case is closed. Keep your notebook handy and remember the rules. An agent is only as smart as the policy and the structure you give it. Let us recap the key takeaways. Cognition is shaped by the combination of few-shot prompting and chain of thought reasoning. Planning requires explicit structure, such as hierarchical task networks and a clear separation of concerns between the planner and the executor. Uncertainty should be managed by treating the world as a partially observable Markov decision process, where information gathering is prioritized. You should also watch out for several red flags. Avoid overplanning with rigid long-term plans that cannot adapt to change. Beware of magic prompt that lack explicit structure, and never ignore the operational cost of your agent's actions. If you follow these principles, you will be well on your way to designing practical and safe and governable agent systems that can excel in any environment. Thank you for participating in this session of the agency course. You now have the blueprints to build minds that can reason and plan and act with precision. Good luck on your next project. If you enjoyed this video, do like, share, and subscribe. Thank you.